Let's do an example involving a charge that has cylindrical symmetry. Charge is spread uniformly along a long, thin wire. The charge per unit length on the wire is lambda and is constant. Find the electric field at a distance r from the wire, far from either end of the wire. Well, let's look at this. Our goal is to find the electric field at some arbitrary distance r away from the wire. Let's start by drawing our wire. Here's our wire of charge. And we know that charge is uniformly distributed along this wire. The density of this charge is lambda. We need to find the electric field at a point r away from the wire. So that'll be our arbitrary point. We will say this is a point r away from the wire. Now, this point has to be far from the end. And we have to find the electric field at that point. How do you think we could do that? Well, let's look at Gauss's law. Gauss's law says that the electric flux through a closed surface is equal to how much charge is enclosed by that surface over epsilon naught. Okay, so what do we mean by this? Well, first let's look at the notation. This circle on the integral corresponds to a closed surface. What that means is the surface completely contains a volume. So let's say, imagine a container that's filled with water. No matter how you shake that container, the water will stay inside the container if the container is closed. Nothing can get out, nothing can get in. Same thing with the closed surface. Our surface has to be completely closed, separating a volume outside the surface from a volume inside the surface. And let's look at this charge enclosed. This is how much charge is inside the surface. So how much charge is inside the surface? You can think of it as being trapped. Again, using that water analogy, no water can get in or out. No charges can get in or out of the surface. Here's the beauty of Gauss's law. The beauty of it is by calculating a surface integral of an electric field over a closed surface, we could determine exactly how much charge is inside that surface. And now the problem with this, though, is Gauss's law involves an integral. However, for electric fields that are symmetric to some surface, it'll just so happens that the electric field, if we could find a surface where the electric field is uniform or constant in magnitude and constant in direction relative to that surface, then we can avoid integrating. Or let me rephrase that. Our integration becomes much simpler if the electric field is constant relative to the surface. So let's write that down. For E fields that are constant relative to a surface, then the integral becomes, I'm going to say, trivial. You'll see how that plays out. So how do we find electric fields that are constant relative to a surface? Well, look for symmetry. Remember, if a charge configuration is symmetric, then the electric field will be symmetric. Let's use this fact. Let's see if we could find a surface that is symmetric about this line of charge. Because if we could find a surface that's symmetric about the line of charge, we could determine the electric flux, which means we could determine the electric field. So that's our task. Find or choose a surface that's symmetric to the charge. We have to choose a surface or find a surface that matches the symmetry of this long line of charge. Now, you might remember that a long line of charge is cylindrically symmetric. Remember, what cylindrically symmetric means is if we take a cylinder that is centered about that line of charge, that our electric field will be symmetric relative to that cylinder, relative to the line of charge. So let's take a cylinder that has a radius given by the distance between the point and the line of charge. This cylinder is our Gaussian cylinder. It is not a real surface in space, it's a mathematical surface in space. Gaussian surfaces don't have to be real surfaces. Now, in order to do Gauss's law, we're going to have to enclose a certain portion of this charge. And so since we're going to have to enclose the charge, this cylinder is going to have a closed left end. That left end is going to be completely closed. It's going to have a closed right end, and the sides are closed. So there's really three surfaces here: the side, the left end, and the right end. Now you can see from this that this Gaussian cylinder is cylindrically symmetric with respect to the electric field, or we could say the electric field is cylindrically symmetric because the electric field looks the same everywhere on this Gaussian cylinder. If we take just another vantage point to better illustrate that, let's look at from one end of our line of charge. Notice that the electric field relative to the surface has the same magnitude on any point of that surface, and relative to a tiny bit of area on that surface, the electric field is always parallel to a tiny area differential. That's going to be a useful thing for us. Well, now that we can see that the line of charge and therefore the electric field has cylindrical symmetry, let's apply Gauss's law. Gauss's law says that the electric flux through a closed surface is equal to the amount of charge enclosed by that surface over epsilon naught. Well, let's draw what we mean. Here's our surface. And here's the charge enclosed by that surface. Okay, there's charge outside of the surface. But Gauss's law is really only concerned with the amount of charge inside or contained within the volume of that surface. Now, this surface has three sides. It has a left side. It has a right side. And I'll just call the side the side. If we look at different surfaces, let's look at the area of each surface. So the left surface is going to have an area vector that is perpendicular. I'll just call this A sub L for the area of the left surface. Now you might be wondering, well, why do we need the area? Because Gauss's law involves an electric field in an area differential. Knowing the relationship between the electric field and the area vectors is crucial for being able to solve this problem. So the area of the right cap I'm drawing to the right, and I'll just put vectors here to remind myself that these are area vectors. And technically their area differentials is what we should be looking at, because we're looking at very tiny pieces of area for our integration. And then for the side, the area differential, I'll just call this DAS, S for side. Now let's look at the electric field that crosses each of those surfaces. So remember, this line of charge has cylindrical symmetry. So I know the electric field will be radially pointing away from the line of charge such that it's perpendicular to our cylinder. Now, drawing it from this vantage point, you could be forgiven for thinking that the electric field is uniform, but it's not. If we just chose a different vantage point, again, you would see that the electric field is just radially away from the line of charge. So even though the electric field isn't uniform for all points in space, at any point on this sphere of radius r, cylinder of radius r, relative to the surface of the cylinder, that side surface of the cylinder, the electric field is constant in magnitude and constant in direction relative to our tiny area vectors. And relative to the left and right ends, the electric field vector at that point is perpendicular to our area vectors. I'm using subscript EL for the electric field at the left end, ER for the electric field at the right end. And I'll use just ES for the electric field through the side. All same magnitude, but I like to distinguish between them because it'll help the integral. Now let's find the electric flux. The electric flux is given by Gauss's law, which says that the closed surface integral of the electric field is equal to the amount of charge inside that electric field over epsilon naught. So the amount of charge, that's this here, Q enclosed. We don't include anything outside of the cylinder. Well, let's look at this surface integral. So this closed surface integral can be done by summing up over each of the surfaces. Summing up over the left surface, the electric field passing through the left surface times the area vector on the left surface, plus the right surface, the electric field passing through the right surface, dotted with the area vector of the right surface, plus the side, where we have the dot product between the electric field on the side with the area vector on the side. And all of this has to be equal to how much charge is contained by that closed Gaussian surface over epsilon naught. Well, let's look at each of these. Remember, the dot product of two vectors that are perpendicular to each other is equal to 0. Well, how do I know that? Well, let's turn to the definition of the dot product. If we look at the electric flux through the left cap of the cylinder, this would be equal to the magnitude of the electric field through the left cap times the magnitude of the area vector through the left cap times the cosine of the angle that the electric field makes with the area vector through the left cap. This is from one of our versions of the dot product. Let's add this to the electric flux for the right cap. So that is the integral of the magnitude of the electric field for the right cap times the surface area differential for the right cap times the cosine of the angle between the electric field and the area for the right cap. And let's do it for the side. The electric flux through the side is equal to the magnitude of the electric field through the side times the area differential through the side times the cosine of the angle between the electric field and the area differential through the side. Well, remember from our picture that the angle between the electric field and the left end, this angle is 90 degrees. The cosine of 90 degrees is 0. So remember, two vectors that are perpendicular, their dot product is going to evaluate to 0 because the cosine of 90 degrees is 0, which means there is no electric flux mathematically. Now we see that from the picture though. Conceptually, no electric field lines are crossing the plane of the left surface. Since no electric field lines are crossing the plane of the left surface, the electric flux through that surface must evaluate to 0. Same thing with the right surface. Since there are no electric field lines crossing the plane of the right surface, and that's true because the angle between the electric field and the right surface is 90 degrees, because that angle is 90 degrees, we know that the electric flux through the right surface is going to be 0. This means we are left with the electric flux through the side of our cylinder. The electric flux through the side of the cylinder is given by the magnitude of the electric field through the side of the cylinder times the cosine of the angle between the electric field and the area differential through the side times the area differential of that side. Well, the cool thing is, referring back to our picture, notice that the angle between the electric field and a side area differential, that angle is 0 degrees no matter where you are on a side. Cosine of 0 degrees is 1. Well, that's great. Cosine of 0 degrees is 1. This term evaluates to be 1. Now, remember, the electric field on our cylinder is constant in magnitude everywhere on the cylinder. So that constant comes outside of the integral. We're left with just the integral over the surface of our area differential. Well, the integral of that area differential is just the area of that surface. This is what I meant earlier when I said that the electric field will evaluate in almost a trivial way. Because we chose a Gaussian surface that is symmetric with the charge, the amount of work we had to do for integrating becomes very, very easy because our electric field is constant relative to our area differentials on our surface. Now, we're not done yet. The problem said find the electric field at a distance r from your wire far from either end. But we're getting there. Well, what is the area of a cylinder? That's what AS is. You might remember that the area of a cylinder is equal to the circumference of the cylinder, 2 pi times the radius r, times the length of the cylinder. Okay, so we have to go back and look at our length. Well, that picture's kind of messy. Let's just go ahead and redraw our cylinder down here and just focus on the cylinder part itself. So our Gaussian cylinder has a length L. We're not given that length, but you're going to see we're not going to need to know the length of that cylinder. So it has a length L, a radius R, and this is enclosing a certain amount of charge. So our area then is given by 2 pi times the radius times the length. This means we could write that the product of the electric field and the area of that side is equal to how much charge that is enclosed by that surface over epsilon naught. So the electric field is equal to the amount of charge enclosed by that surface over 2 pi r epsilon naught L. Well, we are really close to having an expression that is for the electric field at a distance r away from the charge. There's our r in our answer, but there's two things we don't know. We don't know how much charge is enclosed, and we just picked an arbitrary length for the cylinder. We don't know the length of the cylinder. We don't know how much charge we're enclosing. But what we do know is that the density of charge is a constant. the linear charge density, remember, is defined as dq over dl. Because lambda is constant for a uniform charge distribution, dq over dl, the charge per unit length, is constant. So we could write this as q over L. And since charge per unit length is constant, and since we have a certain amount of charge that is enclosed for a certain length, we get that lambda is equal to q enclosed over L. Or, rewriting this, we get the amount of charge that is enclosed by our Gaussian surface is equal to lambda L. Well, this means then that the electric field through that side at a distance from r away from our line of charge is given by lambda L over 2 pi r epsilon naught L. But the L's cancel, and now we have a function for the electric field. That the electric field, as a function of r, is given as lambda over 2 pi epsilon naught, and I'll put the 1 over r here. And let's express this as a vector. So this is along a radial axis relative to the axis, the central axis of the cylinder. Here is our electric field at any point r away from the line of charge. Notice that this expression here is just a constant. And this says that the electric field, due to a long line of charge, varies inversely with distance.